June 19, 1944, Philippine Sea, Western Pacific. The morning sky was clear above a thin stratus layer. Wind direction was steady from the east at 12 knots. Visibility exceeded 20 miles. Below, the ocean appeared calm, reflecting scattered cumulus fields. At 9:45 hours, radar operators aboard the USS Lexington detected multiple incoming groups. Bearing 210, distance 150 miles, altitude estimated 15,000 feet. The alarm was transmitted through the Task Force 58 communication network. On carrier flight decks, crews prepared intercept waves. The first group of F6F-3 Hellcats launched at 9:57. Propellers spun under full throttle, producing dense exhaust clouds. Each aircraft carried 6.50 caliber Browning M2 guns and a full ammunition load. Wingtip recognition lights blinked as pilots formed into combat divisions. The engine noise was uniform, steady, and deep. In the opposite direction, Japanese carrier air groups from Shokaku, Zuikaku, and Junyo formed outbound overcast formations. Their aircraft, mainly Mitsubishi A6M5 Model 52 Zeros, carried 330 liters of fuel each and limited radio equipment. Altitude climbed to 17,000 feet at an average rate of 2,800 feet per minute. Formation spacing was precise, 20 meters between aircraft, 100 between elements. At 10:23 hours, contact was established. American radar controllers issued vector headings to interception squadrons. Hellcats from Yorktown and Enterprise ascended through broken cloud layers. Rate of climb exceeded 250 feet per second. The Pratt & Whitney ARD-2800 engines produced a metallic resonance audible across several miles of sea surface. At 10:35, Japanese pilots sighted contrails approaching from below at steep angles. Lieutenant Commander Tokahoshi, leading the second wave, ordered formation split to defensive pairs. Each Zero executed a shallow turn to port to gain spacing. The maneuver was clean and coordinated. However, the intercepting Hellcats reached altitude sooner and maintained higher energy. The first visual encounter occurred near 18,000 feet. Two Hellcats approached from below the sun, attacking at high speed. They fired short, controlled bursts and continued upward without turning. Japanese pilots attempted to follow but could not maintain climb angle. The Zero's engine temperature reached critical levels during the pursuit. At 10:42, radio transmissions from Zuikaku reported fragmented formations. Engagements lasted seconds. American fighters used vertical attacks, diving from altitude, firing, then climbing away. Japanese aircraft, optimized for turning combat, found no opportunity to engage horizontally. Observers aboard Yorktown recorded gun camera footage. Frames later analyzed showed Hellcats maintaining attack energy even after repeated passes. Zeros displayed tighter turn radii but lost altitude and speed with each maneuver. The contrast was distinct and measurable. By 11:20 hours, scattered oil fires appeared on the sea surface. Several Japanese aircraft ditched after fuel exhaustion or damage. Rescue planes launched but recovered few survivors. Radio silence was ordered across the Japanese task group. Onboard Lexington, deck crews retrieved returning aircraft. Many bore bullet holes and heat discoloration, yet engines continued operating. Armor plating behind pilot seats showed impact marks without penetration. Data plates recorded sortie durations, ammunition expenditure, and altitude bands. By midday, the operational outcome was clear. Intercept formations achieved air superiority before the enemy reached carrier range. The Japanese attack waves failed to inflict significant damage. Intelligence officers began compiling immediate after-action reports. Observations emphasized climb rate, acceleration, and altitude control as decisive variables. The recorded facts indicated that aerial combat had transitioned from maneuver-based engagements to energy-based dominance. As the sun reached zenith, the remaining Zeros retreated westward. Their engines emitted trails of smoke from sustained overheat. The horizon remained dotted with small black columns marking aircraft impacts. Throughout Task Force 58, the radio traffic reduced to brief status confirmations. The battle's measurable evidence, altitude data, fuel records, and gun camera film had already demonstrated a fundamental shift in aerial warfare. On that day, speed and power had proven superior to agility and lightness. The contrast, observed directly by every pilot involved, marked the moment the age of turning combat ended. By mid-1944, the Imperial Japanese Navy Air Service operated under conditions of declining material strength and reduced pilot proficiency. The A6M Zero, first introduced in 1940, had achieved superiority through its lightweight design and exceptional range. Its empty weight averaged 1,800 kilograms, nearly one-third less than contemporary American fighters. This advantage allowed long-range patrols and agile maneuvering during early Pacific campaigns. However, the aircraft's structural philosophy prioritized lightness over durability. The absence of armor plating and self-sealing fuel tanks left pilots vulnerable. Fuel lines and wing tanks were unprotected. Minor hits often ignited fires that spread rapidly through the fuselage. These design decisions, once acceptable for tactical dominance in 1941, became liabilities as Allied aircraft evolved. By contrast, the Grumman F6F Hellcat embodied a new standard in naval aviation. First deployed in 1943, it represented the culmination of lessons learned from previous Pacific engagements. The Hellcat weighed over 4,000 kilograms but maintained superior climb and acceleration due to its A2800 double Wasp engine, producing 2,000 horsepower. Its maximum speed reached 380 miles per hour at 23,000 feet, exceeding the Zeros by nearly 60 miles per hour. Grumman engineers adopted a design approach emphasizing strength and power rather than minimal weight. The aircraft featured 12.7 millimeters of armor behind the cockpit, bullet-resistant windshield glass, and self-sealing fuel tanks. Its landing gear and control surfaces were hydraulically reinforced for high-speed dives and carrier recoveries. Operational reports from the U.S. Navy Bureau of Aeronautics confirmed that the Hellcat sustained damage yet remained controllable, even with major system failures. By 1944, American naval aviation strategy shifted from small-scale interception to extended-range power projection. The creation of Task Force 58 allowed simultaneous carrier operations across thousands of miles. Each task group carried hundreds of aircraft, including fighters, bombers, and torpedo planes. Combat information centers coordinated radar tracking and vector guidance. Engagements occurred beyond visual detection range, guided by instrument and radio. The Japanese system relied heavily on visual spotting and pilot initiative. Radar coverage remained limited to experimental sets aboard major carriers. Without electronic detection, Japanese formations launched preemptively, often at disadvantageous altitudes. When contact occurred, American aircraft already possessed positional and energy superiority. In terms of production, the industrial imbalance was significant. American factories produced aircraft in quantities Japan could not match. Between 1943 and 1944, Grumman's Bethpage facility delivered over 6,000 Hellcats. Mitsubishi's total Zero output during the same period fell below 3,000 units due to shortages in aluminum, fuel, and skilled labor. Strategically, Japan's doctrine continued to value close-quarters maneuvering. Training emphasized turning combat, wing coordination, and gunnery accuracy. This approach aligned with the Zero's original advantages but ignored the changing technical environment. The United States, observing combat data from the Solomon Islands and New Guinea, modified its pilot instruction programs. The thatch-weave and high-side attack maneuvers prioritized speed retention, altitude control, and coordinated defense. These methods converted horsepower into tactical dominance. Japanese analysts at the Yokosuka Naval Technical Arsenal recognized the implications. Reports filed in early 1944 mentioned energy-based tactics and a vertical combat advantage. However, design limitations of the Seiki 21 engine, producing 1,130 horsepower, restricted adaptation. Overheating and mechanical failure occurred when attempting to match the Hellcat's sustained climb rates. Thus, by the time of the Battle of the Philippine Sea, both forces entered combat representing two distinct technological doctrines. The Japanese relied on pilot agility and maneuver precision. The Americans relied on speed, climb, and endurance. The result was predictable through physics rather than tactics. The side with greater mechanical energy controlled altitude, initiative, and survival. After the Battle of the Philippine Sea, surviving Japanese officers and engineers initiated a systematic technical review. The goal was to determine why combat losses had reached unprecedented levels despite experienced personnel and disciplined formations. The Naval Air Technical Arsenal at Yokosuka received several damaged aircraft recovered from forward bases, including partial wreckage of both A6M Zeros and captured components from downed F6F Hellcats. Inspection teams began disassembly procedures under Directive No. 1342, dated July 2, 1944. Each section of the aircraft was measured, photographed, and logged. The first comparative study concerned fuselage strength. The Hellcat's main frame used thicker gauge aluminum, with additional reinforcement around the engine mount and cockpit bulkhead. Rivet spacing measured 8 mm closer than in the A6M. This structure allowed higher aerodynamic loads without deformation. The Zero's lightweight frame, by contrast, exhibited buckling under test stresses exceeding 6 G. The next evaluation involved protection systems. The Hellcat's pilot armor plate measured 12.7 mm in thickness, composed of hardened steel. The Zero possessed none. Self-sealing fuel tanks in the American fighter used layered rubber compounds capable of closing small-caliber punctures. Japanese engineers attempted to reproduce the method but lacked comparable rubber and fuel-resistant adhesives. Engine analysis provided the most critical data. The Pratt & Whitney R2800 Double Wasp was retrieved from a damaged Hellcat at Saipan. Engineers documented every major component, supercharger stages, intercooler ducts, and exhaust manifolds. Dimensional precision was within a tolerance of 1/1000th of an inch, a figure unmatched by Japanese mass production at the time. The two-stage mechanical supercharger provided consistent manifold pressure across altitude ranges, maintaining full power beyond 23,000 feet. In contrast, the Nakajima Seiki 21 engine displayed rapid loss of power above 18,000 feet. Its single-stage supercharger lacked the capacity to compress thin air efficiently. Engine test runs conducted at Yokosuka under controlled conditions showed that the Seiki sustained full power for 70 hours before overhaul. The American R2800 maintained performance beyond 150 hours. Fuel quality compounded the issue. American aviation fuel contained octane ratings of 100 to 130, allowing higher compression ratios and ignition advance. Japanese fuel rarely exceeded 87 octane. Comparative combustion tests demonstrated detonation and temperature spikes in domestic engines at similar power settings. This restricted the Zero's climb rate and top speed during prolonged engagement. Flight test simulations were conducted using captured data. Engineers used training aircraft to mimic Hellcat climb profiles. Even under ideal conditions, test aircraft could not maintain pursuit beyond 6,000 meters. Acceleration losses occurred within 20 seconds of level flight comparison. The Naval Technical Bureau documented these results in a report titled Comparative Characteristics of Domestic and Allied Naval Fighters, filed August 1944. Charts showed consistent advantage in power-to-weight ratio, energy retention, and altitude control for the Hellcat. Analysis concluded that Japan's design philosophy had reached a physical limit. Lightweight structures and minimal protection, once advantageous, could not compensate for increasing engine disparity. The new air combat environment favored mass, horsepower, and vertical energy control. By late 1944, technical officers formally adopted the term energy warfare to describe the new reality. The phrase appeared in internal memoranda distributed to senior command. It summarized a fundamental observation: air superiority no longer depended on pilot agility alone, but on mechanical power sustained through altitude and climb. By October 1944, Japanese Naval Air Command formally acknowledged a tactical shift it could no longer counter. The evidence collected from both combat reports and engineering studies indicated a single, measurable truth: engine power and climb capability now dictated survival. Field debriefs from returning pilots provided consistent testimony. One recorded statement read, "The enemy ascends without limit. Our engines overheat before contact." These words were entered directly into the 5th Carrier Division's operational record. Another report, from the 601st Air Group, stated that engagements ended before Japanese aircraft could achieve gun range. The Hellcats initiated attacks from superior altitude and speed, withdrawing vertically before retaliation. Data compiled from gun camera films supported these observations. Analysts documented average engagement durations of less than 30 seconds. The Hellcats maintained a consistent energy advantage through climb and dive cycles. Zeros, forced into tight turns to evade fire, lost altitude and momentum with each maneuver. Once below the initial altitude band, recovery became impossible against opponents still accelerating upward. This operational imbalance forced a doctrinal reassessment. For years, the Imperial Japanese Navy had trained its pilots for horizontal dogfighting, close turns, precision gunnery, and situational awareness. Now, those techniques provided no measurable advantage. The Zero's high roll rate and low stalling speed could not compensate for inferior acceleration or durability. At Atsujai and Yokosuka, tactical instructors revised lesson materials. New diagrams emphasized energy retention rather than returning superiority. Pilots were instructed to avoid prolonged maneuvers and maintain altitude whenever possible. Yet, the aircraft themselves were incapable of sustaining the prescribed performance envelope. Repeated flight tests demonstrated overheating and mechanical strain during steep climbs lasting more than 60 seconds. A technical memorandum dated November 1944, issued by the Naval Air Technical Bureau, summarized the situation: present aircraft unable to perform in vertical combat regime. Future designs must prioritize power output and protection. The statement marked a fundamental departure from previous doctrine. Attempts to implement the lesson followed quickly. The Nakajima Keel 84H8 and Kawanishi N1K2, the J. Shidenkai incorporated heavier frames, more powerful engines, and armored fuel systems. However, engine reliability and material shortages limited operational success. The new aircraft entered service in small numbers and too late to affect overall outcomes. Frontline squadron records reveal the effect of this realization on combat readiness. Pilot attrition increased as inexperienced replacements entered service with minimal training hours. The new energy-based tactics demanded precision in throttle management, climb timing, and gunnery under high acceleration. Without standardized instruction and reliable aircraft, implementation failed. By January 1945, internal assessments of the combined fleet documented a decisive change in combat character. Air battles no longer consisted of prolonged turning duels. Instead, they became brief, vertical exchanges where speed and horsepower determined outcome within seconds. The phrase "power as defense" appeared frequently in post-action summaries. It described the Hellcat's ability to climb away from danger or absorb damage without loss of control. The Zero, though agile, disintegrated under comparable stress. From this accumulation of technical data and combat observation, Japanese command concluded that agility had ceased to define air superiority. In its place stood measurable power, altitude control, and structural endurance, the attributes embodied by the F6F Hellcat. By early 1945, the shift from maneuver-based to power-based aerial warfare was complete. The evidence existed not only in combat outcomes but in the underlying industrial structure that sustained each side's air forces. American aircraft factories operated continuously under coordinated production schedules. Grumman's Bethpage plant produced nearly one F6F Hellcat every hour by the summer of 1944. Subcontractors across the United States supplied standardized components, ensuring mechanical uniformity and interchangeable parts. In Japan, production was fragmented. Aircraft assembly relied on dispersed workshops and manual fitting. Bombing of Yokosuka, Nagoya, and Musashino reduced engine output by more than half. Each Zero required extensive hand finishing, consuming skilled labor and time. Component quality varied between production batches, complicating field maintenance. The structural strength that defined the Hellcat's durability was impossible to reproduce under these conditions. Fuel quality further reinforced the divide. The U.S. Navy's 130 octane aviation gasoline enabled engines to operate at higher manifold pressures without detonation. Japanese refineries, dependent on low-grade crude and limited additive supply, produced fuel averaging 87 octane. This limited the Seiki engine's ability to generate continuous power during climbs or dives. Technical memos from the Naval Air Technical Bureau explicitly connected fuel octane deficiency to altitude loss and overheating. Operational doctrine reflected these industrial realities. The U.S. Navy's Task Force 58 employed integrated carrier logistics groups. Oilers, ammunition ships, and repair vessels accompanied combat formations, providing uninterrupted support. Replacement aircraft arrived within days. In contrast, Japanese carriers operated without equivalent resupply infrastructure. Aircraft lost in combat were seldom replaced before the next sortie. Strategic data compiled by both navies demonstrated the results. Between June 1944 and March 1945, Japanese carrier-based air units lost approximately 90% of their operational aircraft. American losses in equivalent operations remained below 10%. These figures appeared in official after-action analyses conducted by the Imperial Navy General Staff and confirmed by post-war U.S. naval records. Technical evaluations by the U.S. Navy Bureau of Aeronautics credited the Hellcat's design philosophy with sustaining such operational superiority. The combination of armor, redundant hydraulics, and robust landing gear allowed repeated carrier operations without mechanical fatigue. Each aircraft averaged more than 250 flight hours before overhaul. The Zero, by contrast, required major inspection after 70 hours due to structural stress and engine wear. Captured Japanese documents later examined by the U.S. Naval Technical Mission to Japan, 1945-46, revealed an internal acknowledgement of this disparity. Engineers described the psychological impact of seeing enemy aircraft climb through clouds unimpeded while their own engines overheated. One report stated plainly, enemy aircraft displays continuous power, unaffected by altitude. By this period, Even new Japanese fighter designs such as the A7M Repu and N1K2 the J Shidenkai failed to change the operational equation. Production bottlenecks, fuel scarcity, and limited pilot training rendered them strategically irrelevant. The industrial balance had become irreversible. The transformation observed in the Pacific reflected a broader global pattern. In Europe, aircraft like the P-51 Mustang and FW-190 demonstrated similar trends, superiority defined by engine performance and energy retention rather than maneuver agility. Across all theaters, the determining variables became climb rate, speed, and mechanical endurance. In quantitative terms, the Pacific Air War had become an experiment in applied physics and logistics. The nation capable of sustaining horsepower, fuel supply, and production rate achieved dominance. By 1945, that nation was the United States. The once celebrated agility of the Zero had been overtaken by industrial power, material science, and the measurable mathematics of energy warfare. After Japan's surrender in August 1945, Allied technical missions entered the country to collect surviving aircraft, engines, and research documents. The U.S. Naval Technical Mission to Japan, JAP then A02 through JAP N13, catalogued more than 3,000 engineering files, factory blueprints, and flight test records. Investigators interviewed former officers from the Naval Air Technical Arsenal, Mitsubishi Heavy Industries, and Nakajima Aircraft Company. Their testimonies confirmed the conclusions already drawn in combat: mechanical energy, not maneuverability, now defined aerial superiority. Post-war studies compared quantitative performance across both nations' fighters. The A6M Zero achieved a maximum climb rate of 3,100 feet per minute and a top speed of 351 miles per hour. The F6F Hellcat climbed at 3,500 feet per minute and exceeded 380 miles per hour while maintaining combat load. The difference appeared modest on paper but proved decisive in sustained engagements. The Hellcat could absorb damage, dive faster, and regain altitude more efficiently. The Zero, lacking armor and self-sealing tanks, often failed after minor hits. American analysts summarized the operational contrast through attrition data. By war's end, Hellcats had achieved 5,156 aerial victories with 270 losses in air combat. The official kill ratio exceeded 19-1, verified by the U.S. Navy Bureau of Aeronautics. Japanese squadron records, cross-checked after the war, reflected similar proportions. Technical engineers from both sides collaborated briefly during post-war testing. Captured Zeros were flown at NAS Patchesant River, Maryland. U.S. test pilot Lieutenant Commander Eric Brown conducted several flights under controlled conditions. His evaluation, filed as report number 27-45, concluded, aircraft displays superior turning ability at low speed, but structural fragility and insufficient power restrict combat application against current types. The document became a reference in post-war fighter development programs. In Japan, academic institutions integrated wartime data into peacetime study. Tokyo Imperial University and Nagoya Technical College established aeronautical departments to analyze the causes of wartime losses. Former Navy engineer Kenji Yoshida authored a study of power dominance in aerial combat in 1949. The report stated, the determining factor in aerial warfare lies in continuous power output and structural endurance. Agility without energy is temporary advantage only. His analysis reflected the consensus among surviving engineers. Globally, aircraft design philosophy shifted to match the findings. New jet-powered models emphasized thrust, speed, and durability. The lessons learned from the Hellcat Zero confrontation directly influenced Japan's first post-war jet project, the Fuji Ts-1, which adopted reinforced structures and high-power engines. Archival evidence indicates that the Japanese aviation community accepted these conclusions without dispute. Official summaries from the Naval Air Technical Bureau, declassified in 1953, describe the Zero as a masterpiece of light construction suited to an earlier tactical period. The same documents identified the Hellcat as representative of the new principle of energy warfare. Historians reviewing these materials later defined the Battle of the Philippine Sea as the point where air combat entered the energy era. Engagements were no longer contests of agility but of acceleration, altitude, and mechanical endurance. The Japanese pilots who had once dominated through precision and maneuver witnessed the change directly. During the final year of the Pacific War, their aircraft could turn faster but not climb higher, could evade briefly but not endure. Speed, power, and altitude dictated every outcome. Post-war reflection among both Allied and Japanese engineers aligned on a single, verifiable conclusion. The Second World War had transformed the meaning of air superiority. From 1944 onward, victory in the sky depended on horsepower, structure, and fuel, factors measurable, repeatable, and industrially scalable. The era of lightweight dogfighters ended with the fall of the Zero. In its place began the era of energy warfare, first proven above the Philippine Sea when F6F Hellcats climbed beyond reach and demonstrated that speed had permanently replaced agility as the decisive element of air combat.